Hello everyone, myself Crystal, currently studying in Sri Venkateshwara College of Engineering in Department of CSE AI. In this video we will learn about computing error and approximation. Introduction. Importance of numerical computations. Numerical computations are indispensable for solving complex problems, optimizing designs, simulating systems, and ensuring the safety and efficiency. Understanding errors and approximation to ensure accurate results. By thoroughly understanding and managing errors and approximations, we can ensure that numerical computations yield reliable and accurate results. Let's move on to types of errors. First one is round-off error. This error results from finite precision limitation of computers, which can only represent numbers with a certain number of significant digits. As a result, small discrepancies occur when numbers are rounded to fit within the available precision. For example, storing the number pi as 3.14 instead of its full infinite decimal representation. The next error is truncation error. This error arises when an infinite or continuous process is approximated by a finite or discrete process. For example, when numerical methods approximate derivatives or integrals using a finite number of steps or terms. Another example is using a finite number of terms in Taylor series expansion to approximate a function. The next error is absolute error. The absolute error is the magnitude of the difference between the exact value and the approximate value. It measures the size of the error without regard to its direction. Example, if true value is 10 and the approximate value is 9.8, the absolute error is magnitude of 10 minus 9.8, which is equal to 0.2. The next error is relative error. The relative error is the absolute error normalized by the true value, providing a measure of the error relative to the size of the true value. It helps in understanding the significance of the error in context. For example, if true value is 10 and the approximate value is 9.8, the relative error is 0.2 by 10, which is equal to 0.02 or 2%. Sources of error. Input data error. This type of error arises when the input values provided to a numerical computation are inaccurate or imprecise. These inaccuracies can result from measurement errors, data entry mistakes, or limitations in data collection methods. For example, using an imprecise measurement of a physical quantity such as length or temperature in a calculation. Algorithmic error. Algorithmic errors are inherent to the numerical methods or algorithms used in computations. These errors result from the design or implementation of the algorithm, such as using an approximation method or iterative process that introduces some level of error. For example, approximating the value of a definite integral using numerical integration methods like the trapezoidal rule or Simpson's rule. Propagation of error. This occurs when errors from initial stages of a computation carry over and affect subsequent calculations. As numerical computations often involve multiple steps, small errors can accumulate and potentially magnify, leading to significant inaccuracies in the final result. For example, in iterative methods like the Newton-Raphson method, errors in initial guesses can propagate through iterations and impact the convergence of the solution. Approximation techniques. Taylor series approximation. A method to approximate functions by expanding them around a point using the derivatives of the function at that point. The Taylor series is particularly useful for approximating functions that are smooth and differentiable. For example, approximating e power x around x is equal to 0 using the series e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Finite difference approximation. A technique used to approximate derivatives by using differences between function values at discrete points. It is commonly used in numerical differentiation and solving differential equations. For example, the first derivative of function f of x at point x can be approximated using the finite difference method. f dash of x is equal to f of x plus h minus f of x divided by h, where h is a small step size. Minimizing errors. Choosing appropriate methods. Selecting the right numerical method is essential to minimize errors. Different methods have different error characteristics, and choosing a method that suits the problem at hand can greatly reduce errors. Consideration of problem type, error sensitivity of the method, conditioning of the problem. Increasing precision in calculations. Increasing the precision of the calculations can reduce round-off and truncation errors. Throughout this may come at the cost of computational resources. Floating point precision. Using arbitrary precision libraries, working with reduced precision for intermediate steps. Error estimation and setting bounds. A critical aspect of minimizing errors is knowing how to estimate and bound the errors that occur during computations. By understanding the potential errors in a computation, it is possible to apply corrective measures or adjust methods to achieve desired accuracy. Error estimation, truncation error or round-off error, setting error bounds, comparing different approximations. Error analysis. Error analysis is a critical component of numerical computations, allowing us to understand the accuracy and reliability of the results. It involves identifying, estimating, and minimizing errors that arise during computational procedures. There are two main approaches to error analysis: a posteriori analysis and a priori analysis. Error analysis. A posteriori analysis. Error estimation after computation. A posteriori error analysis helps to assess the quality of the computed solution and provides an estimate of how much the result deviates from the true solution. It is particularly useful when the exact solution is not known, but an approximate error bound can still be established. A priori analysis. Theoretical error estimation before computation. A priori error analysis provides a theoretical estimate of the error in the solution based on the properties of the method and the function involved. It is typically used to predict how the error behaves as function of problem parameters such as step size or number of iterations before the computation starts. Thank you all for watching the video.